To the lecture on chapter 26, where we're going to discuss the properties of light. This is the first of quite a few chapters that we actually spend discussing light because there's a lot to talk about. But here we're going to start with the basics. Okay? So we're going to kind of pick up where we left off on electromagnetic induction and talk about how electromagnetic waves are light. We'll talk then about the full light spectrum, including visible light and lots of invisible light. We'll then talk about how transparency works, like in glass, how some materials are opaque, and then a little bit about how the human eye detects light. All right, let's get to it. So, light is the only thing we can see. All right, so we don't actually see objects; we just see the photons or light waves that reach our eye. It originates from the accelerated motion of electrons. Okay, all light comes from the accelerated motion of electrons. That may be because the electron is bouncing up and down, or maybe just because it's moving in circular motion, because both of those would be common types of acceleration that would naturally happen for electrons. Okay, so light is an electromagnetic phenomenon. All right, it is a combination of a magnetic wave and an electric wave. Okay, here it is. This is the electromagnetic wave that is known as light. It is made up of a oscillating or vibrating electric and magnetic field. Okay. And those two fields are perpendicular to each other, as is shown in this three-dimensional photo here, or diagram, right? We have that, the magnetic field would be in one plane, shown in blue, and then in a perpendicular plane is the electric field. See? So they're always perpendicular to each other. They are, however, in phase. Notice that, right? That the two waves are maxing out at the same point, even though they're perpendicular. Okay? So if an electron vibrates up and down 1,000 times each second, it generates an electromagnetic wave with think about the idea here, okay? None, all right? So the vibrating electron will emit a wave with a frequency that's equal to its vibration rate. So if the electron's going up and down 1,000 times every second, then that means that there would be 1,000 hertz wave that's created, okay? So the frequency of the light wave would be 1,000 hertz. But notice that was not one of our options. We had a period, we had a speed, and we had a wavelength, but we didn't have the one we were looking for, which is frequency. And refer back to the characteristics of waves to recall the relationship between period, speed, and wavelength. Okay? And frequency for that matter. All right? So the whole spectrum, okay, the electromagnetic spectrum, also sometimes called the light spectrum, all right, it's a way of classifying electromagnetic waves according to the frequency. So in the visible spectrum, the lowest frequencies appear red, all right? So that is the longest wavelength. On the other hand, the highest frequencies are violet, right, which is a little bit higher than blue, and that is the shortest wavelength. Higher frequency of light than visible light is ultraviolet, so that's more violet than violet, all right, and that causes sunburns. If you continue past ultraviolet, then you get to X-rays and gamma rays. All right. So that's in the direction of very short wavelength, very high frequency, and that's on this side of the electromagnetic spectrum. Ultraviolet, gamma rays, X-rays. Those are all high energy light. They tend to come from high energy phenomenon, and they can be harmful to humans. On the other side of visible light is all the low energy light, infrared, microwaves, which are, you might think, oh, but they're micro, does that mean they're short? Well, they're short compared to other radio waves. Microwaves are so named because they're the shortest of the radio waves, and then all the other radio waves, okay, which can become very long, even meters or kilometers in length. So the electromagnetic spectrum spans waves ranging from the lowest to the highest frequencies. The smallest portion of the electromagnetic spectrum is what? All right, well, of course, it's visible light. We saw that in the image back here. Visible light is a very narrow band, okay? Because that's just what we happen to see, okay? Why is that what we happen to see? Well, because those are just the colors that are produced by our local sun, all right, our local star called the sun, that then are easily transmitted through our atmosphere. That's it. That's the light that happens to be around, and so we have evolved to see it. Okay? But it's a tiny portion of the overall spectrum. Which of these is fundamentally different from the others? Look at your options: sound wave, light wave, radio wave, X-rays. Okay, hopefully it's obvious. Sound waves. Because sound waves, first of all, they're longitudinal, so there's a big difference there in wave types. After all, light is a transverse wave. And furthermore, it's a mechanical wave. It's not electromagnetic at all. Sound is not electromagnetic. It is mechanical. It is the actual motion of molecules. All right. So, light is transmitted similarly to sound in that you can have a vibration and then that vibrating source creates a wave. In this case, the vibrating source is always going to be a charged particle, usually an electron. Okay? Whereas the vibrating source of sound is just some mechanical vibrating object like a string or a tuning fork. Okay? But since light is electromagnetic, it has to be a charged particle that's vibrating. But that definitely is a similar idea, and the frequency of vibration matches the frequency of the wave that's created, and that's also true of sound. Okay? So, one thing to understand light as it passes through a transparent material is to think of it as a series of absorptions and re-emissions. All right? So if you imagine a very, very thin sheet of glass that somehow is only 3 atoms thick, and you have a wave come in, a wave of light, then the first atom can absorb that light. The energy of the light goes into exciting an electron in the outer orbit of that atom. However, eventually, that electron is going to relax and is going to emit another wave of the exact same wavelength and frequency that was created. Now, sometimes not, because sometimes the speed can go down. And since the speed goes down, what will happen is the frequency will remain unchanged, but the wavelength will change to compensate for the reduced speed. Because remember, speed is wavelength times frequency. So if frequency doesn't change, but speed is decreased, then that means something else has to decrease as well. And what is going to decrease is going to be the wavelength. All right? So as light does slow down due to the process of transparency, we do have a decrease in the wavelength. Okay. Now, the way to think about that is that light is moving in a non-vacuum, because maybe you've heard that light always travels at the same speed in the vacuum. Now, here, the speed of light between the atoms is still the speed of light. It's still c. But the process of the atoms absorbing and re-emitting the light slows down the effective speed of light. And then the process would continue, where the next atom would have an excited electron. Eventually, that electron would relax, emitting light of the same frequency. And then, in the same frequency, in this case, would be the same between these two, but perhaps a longer wavelength than the original. And then eventually, the light is released, and it's passed through our very thin sheet of glass. That is the cartoonish, but a basic understanding of what transparency means in terms of light passing through transparent materials. All right. So to continue, how light penetrates transparent materials such as glass. Okay, so we talked about these ideas, including the time delay. You can go ahead and read this for further understanding on your own. Now, that does mean that the atoms need to be able to have electrons that are capable of getting excited with the right amount of energy to match the energy of the light. We'll talk more about electron excitation levels when we talk about the atom, but suffice to say right now that they're not all available. And given a given atom of a particular substance and the particular electrons that are in the outer shells or orbits of that atom, well, they're going to have particular energies that they can handle, so to speak. Okay? And that means that materials might be transparent to one type of light, but not another. And when I say type, I mean wavelength or frequency. Because if you know the wavelength of light, you also know its frequency. All right? For example, glass, all right, has, when infrared waves reach the glass, they don't pass through, right? Instead, they cause the atoms to vibrate, and that increases the temperature of the glass, all right? Likewise, ultraviolet light will not pass through glass because it will cause the electrons to vibrate, and that also just heats up the glass, but the actual light does not pass through. So in other words, light is able to pass through glass if it's visible light, but ultraviolet and infrared light do not pass through glass. Okay? So as far as that time delay in transparency means that in a vacuum, the speed of light is the constant of the universe, which is 300 million meters per second, or 3 times 10 to the 8 meters per second. All right. And in a gas, it is slightly slower than that, but not much. But in other transparent materials like water, it is only 75% that speed. In glass, about 67% that speed. It does depend on the type of glass. And then one of the slowest speeds out there, a diamond, especially one of the slowest speeds of materials that are transparent to visible light, diamonds, the light only travels at 41% the speed that it would in a vacuum, right? So very, very, very slow. And that's due to the dense structure of the diamond. All right. So strictly speaking, the photons of light incident on glass are, look at your options here. Pause if you need to. So the photons of light incident on glass, right, are not the ones that travel through and exit the other side. Because that photon was absorbed. Its energy became the kinetic energy, well, I'd say more the potential energy of the electron as it got excited to a higher energy state within the atom. And when that electron relaxed, it released a new photon, a new particle, not the same one. Okay? So compared with the frequency of illuminating light on a sheet of transparent plastic, the frequency of light that is transmitted is, think about it, okay? It's the same, all right? The frequency is unchanged. Remember I mentioned that. What does change? The wavelength changes, not F. Okay? So when you have that slower speeds, like the diamond, 41% is at the speed, glass, only 67% the speed in a vacuum, obviously something has to be decreased. It's the wavelength. The frequency is unchanged every time, all right? And it's important to remember that. You can kind of think about it as because the frequency is the rate of vibration. That's getting carried over because to the atoms and the re-emission, that gets preserved, but the wavelength doesn't. It's a consequence of that frequency in this case. The average speed of light is less, right, in glass, right? Okay, so those are transparent materials, but what about opaque materials? Well, most things around us are opaque, right? Certainly more than transparent. And they absorb light without re-emitting it. Books, desks, chairs, the walls of your house, right? Those are all opaque. The vibrations given by light to their atoms and molecules are turned into random kinetic energy, into the internal energy, the heat of those materials. So every opaque object, it has maybe as many photons hitting it as a transparent object, but instead of the photons and their energy passing through, all that energy is trapped inside of the opaque material. All right? Which means they have to warm up, right? So glass, being transparent, would warm up only due to wavelengths that it is opaque to, like ultraviolet and infrared, so it does still warm up. But something that is opaque to, say, all forms of light, including infrared and ultraviolet and visible, well, it'd warm up more because there's more energy. Okay? Metals are interesting. They're an interesting case of an opaque material because they're shiny, right? And the light shining on metals forces those free electrons, because we've talked about how metals have lots of free electrons. That was our premise of understanding the flow of charge called current in a circuit. Where you said, oh, well, metals, they have lots of free electrons, so all those electrons can move freely, all right? Unlike insulators, where the electrons cannot move freely. All right? Well, it turns out that that ability of electrons to move freely means that electrons can vibrate at any frequency of ambient light that's hitting the metal, and then they reflect all those frequencies. The overall effect is, well, a mirrored image in some cases, or at least shiny white light in cases where it's not a perfect mirror. Because the perfect mirror also requires a certain amount of smoothness. All right? So let's compare dry surfaces to wet surfaces. So dry surfaces are going to be brighter because the light bounces off directly and returns to your eye. And so then you're getting more of the energy because it's a direct path, maybe just a single bounce. On the other hand, wet surfaces can have cases where individual photons or packets of wave-like light are trapped inside of the water, bouncing back and forth many times, giving up their energy a little bit in every reflection, and thus the overall effect is less energy getting reflected in a dimmer looking object, right? Which makes it look darker. Okay? So shadows, since opaque objects stop the flow of light, and obviously our bias here, excuse me, our bias here is to consider light as visible light, and we kind of keep going back to that. That's of course what we can perceive. We're not perceiving anything else, including infrared and ultraviolet, just outside the visible range. But the point is that those opaque objects are absorbing that light. It's not passing through, and that means on the other side of the opaque object from the source of the light is a shadow. All right. So let's discuss a little bit about the technical aspects of shadows. Right. So a thin beam of light is often called a ray. We'll talk about rays when we discuss a understanding of optics. Things like lenses and mirrors, concave and convex mirrors. Okay, that is a different chapter. But rays are still a helpful way of thinking about a source of light. When we stand in the sunlight, some of the light is stopped while other rays continue in a straight line path. That's because we cast a shadow, a region where light rays do not reach. Okay? Either a large far-away light source or a small nearby light source will produce a sharp shadow. A large nearby light source produces a somewhat blurry shadow. Okay? That's because some of the light is able to get around the object. All right? Because if you think about a faraway source, all the rays are going to be parallel to each other. Whereas if there's a nearby source that's illuminating our orange, some of those rays are coming in at angles, and some of those angles allow for the light to, get around the orange relative to the backdrop that has the shadow cast on it. Okay? So there is usually a dark part of the inside and a light part around the edges of the shadow. These have special names. They are called the umbra and the penumbra. The total shadow is the umbra, and then the part that has a pen in front of it is the partial umbra, which is the penumbra. All right? So case in point, right? This part here is mostly umbra when the light source is very far away. Okay? But when we move the object further away from the wall, we can clearly see, and I'm going to zoom in on this, we can clearly see the difference between the umbra, the dark shadow, and the penumbra, the light shadow. Okay? You can see in other cases here, there's a small umbra there and a much larger penumbra. Okay? All right, so penumbras are partial blocking of light, so it's a dimming, and umbra is complete blocking of light, so none at all. This is very relevant when we think about celestial events that involve the casting of shadows of the moon and of Earth. So that's the shadow created by Earth and the shadow created by the moon. All right, so in a solar eclipse, the shadow that is created is from the moon. All right, and in that case, there is a umbra and a surrounding penumbra. So when people talk about being in the path of a partial eclipse, that's because they're in the penumbra of the shadow cast by the moon on the surface of Earth. If you are in the path of totality, which is the total eclipse, that means you're in the much smaller umbra. So for comparison, the umbra cast by the moon during a typical solar eclipse is about 70 to 150 kilometers in diameter, whereas the penumbra is about 1,500 to 2,800 kilometers in diameter. Okay? On the other hand, we have a lunar eclipse. A lunar eclipse is when the moon passes through the shadow of Earth, all right? And a total lunar eclipse is when the moon passes through Earth's umbra, and a partial lunar eclipse is when the moon passes through Earth's penumbra. And partial lunar eclipses aren't very noticeable, but total lunar eclipses are quite noticeable because when the moon passes through the penumbra, now there's no direct light reaching the moon from the sun. And so in that case, of course, it has to be a full moon because only full moons can possibly be eclipses. And so that full moon then isn't picking up any reflected light from the sun. Instead, the only light that starts to reach the moon, in the case of a total lunar eclipse, is the refracted, and we'll talk about refraction later, the refracted red light from the ring of Earth's sunsets, and that light is red, thus making the moon appear red during a total lunar eclipse. Okay? So what about seeing with the eye, the human eye? So light is the only thing we can see, right, with the most remarkable optical instrument known, the eye. Right? We haven't outmatched it in terms of engineering. As light enters the eye, it moves through the transparent cover called the cornea, right there. which does about 70% of the necessary bending of the light. That's refraction. It acts as a lens. More on that later. Okay. And then it goes through an opening called the iris. Okay. Then that light is going to be focused on the retina. Okay. As we see, and some other steps involving passing through the crystalline lens in the vitreous humor of the eye. Okay. For clear vision, light must focus directly on the retina. Okay. And if it doesn't, then you might be nearsighted or farsighted if the light is, say, focusing behind or in front of the retina. All right? And the retina itself is composed of tiny antennae that resonate to the incoming light. Okay? So they're picking up those electromagnetic vibrations. The rods handle the vision in low light. They predominate towards the periphery of the retina. The middle of the retina has a special name. It's called the fovea. And the fovea has, in addition to rods, it has cones, which are these specialized cells here. You can see the red on the red there. And they are denser, as I said, in the fovea. And the cones are specialized into 3 groups that can pick up particular regions of the visible light spectrum that are grouped into the red, yellow, and blue. Okay? And so although our vision is poor from the corner of our eye, we are sensitive to things that move because those rods can pick up those small changes in the light signal in our peripheral vision. Okay? And it's an incredible range of light intensity that our eye can detect. So the brightest light that the human eye can perceive without damage is 500 million times brighter than the dimmest light that you can perceive once your eyes, quote unquote, adjust to low light settings. And we don't perceive the actual difference in brightness. The brightest place in our visual field are prevented from outshining the rest, right? So we have these amazingly well adapted, both kind of middle brains that do some of the processing and the eye itself. Okay? And here are some interesting optical illusions in terms of looking at the way that we actually process the information, because we actually don't take in all the information and handle it. We do a lot of shortcuts in terms of brain processing of light. And so it's good to be aware that your vision is not a unbiased view of the world. Instead, it is going through the effective filter that is your brain. So for case in point, the line here is not really broken. It just appears to be so. You can kind of hold your hand across the screen to convince yourself of that. All right. And the dashed lines are not shorter. They are the same length. All right. And then black dots, there are none. If you try to look at one, they go away. They only appear to be in the periphery of your vision. All right. So there are no black dots at the vertices of the squares. Okay. Here is another optical illusion, right? A fun one. All right. And are the rows of tiles really crooked? No, they are not. They just appear to be so. Okay. And it's just the offset that makes them appear. Okay. Are the vertical lines parallel? All right. What do you think? Well, they are, right? They're not concave and convex. They just appear to be so. And there's just some of the many fascinating optical illusions out there that just remind you of how the eye works. Well, more how the brain works. But what have been the main focuses of this lecture? It's been on the idea of transparency and opacity, and the idea that light is part of a broader electromagnetic spectrum. Thank you so much for watching.